Alright, what we're going to do in this video is talk about some examples for path models. So you should have watched the video explaining path models, and then now these are the examples. Alright, click, there we go. So what you want to do is load the chapter 2 R file where I'm going to talk about each one of the commands for it. We're going to look at pages 29 through 31 in the book, and then what we're going to do is sort of ease into this by doing a regular regression in SEM, so in the lavaan code, and an example of mediation through SEM in the lavaan code. So these are things that you could do as regular linear models, but instead we're going to try them as structural equation models just so you can kind of see how they work. So first thing we're going to do is create the data set. So if you don't have the full data, so you're working from, you're trying to replicate something in a book, or you just for some reason only have the correlation matrix, which will happen a lot this semester because most of the examples from the book, they only gave us the correlation or covariance matrix. You can still work with that data. So it's kind of nice because you don't have to have the full data set. There's some things you can't do without the full data set, but for most of what we're doing, we can. And that function in the book says if you have the first printing, it says lower to full. So what they mean is the lower half of a correlation or covariance table to a full matrix of the table. It has been renamed since the printing of the book to lav matrix lower to full. Lower to full still works, it just gives you an error every time and says you should change this. So what you want to do is take the table of correlations and enter them, or covariances, but only the lower half. So let me show you an example. In this I made up a fake correlation table. I know it's a correlation table because if you look here at the ones, so correlation tables always have ones on the diagonal, okay? And then they'll have numbers here that are constrained from -1 to 1. So I don't have any negatives, but you could have negatives, but you definitely won't have like 1.2. A covariance table will have numbers much larger than 1, and the numbers on the diagonal will be variance instead of ones. So in a normal correlation table like that you might get from R, you would also have the numbers up here at the top, the pieces that I've left blank. But in the lower function, what you do is you write each number up to the one or where they are the same. So I'm going to ignore these because they're repeats. So I did 1, 34, 1, 5, 53, 63, 1. Okay. So correlation tables have the ones on the diagonal. Covariance tables have variance on the diagonal. For this particular function, it doesn't matter which not for this function, but for SEM, it doesn't really matter if you're using correlation or covariance. It sort of figures it out for you. And one thing we're going to really focus on this semester is using labels that make sense. So when you have your data, saving this as .cov if it's a covariance table, or .cor if it's a correlation table, and that'll save you a lot of time and trouble later when you're trying to figure out what's going on. Okay. So let's try that. So let me open RStudio here, and I'm going to open my particular file, that chapter 2 file. Move it over here. There we go. Okay, so I have this file. First thing I'm going to do is I'm going to load lavaan and simplot. Okay. So you don't have to install them every time. If you have them installed already, it should just load. Okay. And then let me make this just a little bigger. And what I've got is a correlation table. So for this particular example from the book, it's correlation, so you can see the ones on the diagonal here. And I have stacked my code in a way that I can tell that I've done each one correctly. So if I really wanted to get fancy, I would give each one 2 decimals. So then I could see them line up perfectly. I don't know that that matters so much. But what you want to see is that your half here of this lower half function is a triangle. And you don't want to enter any extra numbers, because if you don't have the kind of a where it'll make a triangle shape, it'll get grumpy with you, because it's expecting a perfect triangle in a sense. And so I've just hit enter after each comma where the line ends, to make sure that I've done this correctly. So let's run that. And what does that do? Well, over here under data, now I have regression.core, and I called it .core just because I know it's a correlation table. And so I click on it. And what that's done is it's created both halves. So it filled in, for variable 1 and variable 2 here, it filled in the 2 over here, 0.24 here, 0.24 here. So it helped fill in the top half of the table by only entering the bottom, because that saves you time. So that's always step 1, figure out your data. You might import a full data set, or you can import from a correlation or covariance table. Sort of step 2 is to give that matrix, because that's what it builds, a name. And really here I should just call this data, but either way. So we're going to take and give it column names and row names at the same time. Okay. So I'm going to come over here. So I did column names of my regression correlation table equals row names of my correlation tables equals, and then I give them names. Okay, and these are from the book. This is a book example directly, so that's why they're called x1, x2, x3, and y. And by hitting enter here, I just know that I've done each one. So you see how it stacks it kind of nicely? So I know that I have put together where it's giving it column names and row names, and it's giving them the same names. So I could do column names equals x1, x2, x3, row names equals x1, x2, x3, but that's a lot of work. Instead, we can do both at once. Now over here under data, I'm going to click on it again, and now you'll see that they each have the right row name and column name. So that allows me to make sure they're labeled correctly, because if they're not labeled both on columns and by rows, for data sets where you enter the covariance or correlation table, lavaan will not run. Okay, so you have to have both. So next thing down, let's make this whole thing bigger here, is to build a model. Well, in the book, it doesn't really give you an example of the picture of this particular model, so I added one. What we're doing is we're taking 3 x's, x1, x2, x3, using all of those to predict y here. So these are exogenous variables. This is an endogenous variable. So because it's an endogenous variable, it has to have an error term. So that's what this is. Now, if I did this perfectly correct, I should add a little 1 right here, right? Because this path is not going to be estimated, but the variance for this bubble will be estimated. Right? We will get the variances estimated for each one of these. So let's think about degrees of freedom for a second. Right? So I've got 4 squares, so I can estimate 4 times 4 plus 1. Right? So that's 5. So 20 divided by 2, that's 10. What am I estimating? 1, 2, 3 parameters here. So 3 parameters, 3 variances, and then this error variance out here. Okay. So you would think, if I drew this model, that we're going to get 7 paths. What we'll talk about here in a minute is what's actually going to happen. And you'll see why this model is kind of a bit of a mess. Alright, anyways, we'll come back to that. But that's the idea, is I have 3 variances, 1, 2, 3, 3 paths, 1, 2, 3, and an error term out here. So the way we're going to build this model is we're just going to do model equals y, because it's being predicted, so y is approximated by x plus x plus x. So 1, 2, 3. Or we can label the parameters. So y equals approximately a times x1. So that's going to give x1's path here just a label of a. It doesn't actually estimate the number any differently. It just labels it in your output as a. B as x2, so that would be here. C is x3. Only thing this does is add labels in your output because we call them different things. If we called both of these A, it would want to estimate them as the same number. Now here's something new, this line. This double tilde, that means variance. So that's going to label the variance of y, the error variance out here, as z. So 2 tildes is variance estimation. Okay, 1 tilde is approximate with. So let's go over here and do that. Okay, so I use the one with labels in my example here. And it's got some little comments in it, but remember that doesn't do anything. It just lets you make comments. All right, so we've imported the data, labeled the data, and built the model. And the labels out here, especially even just this, have to match what's in the matrix of the data. So if these are uppercase, make sure they're uppercase in the matrix. If they're lowercase, make sure they're lowercase. Okay, so we do need to make sure they match. Okay. So you notice that we called this .model. So a lot of times when I'm doing this, I just call it model. But important here in this next step to call it fit. I'll get to why in a second. Okay. So when we run the model, in this particular example, we just have correlation, a correlation table. In the last example that was part of the path video, we did model name, comma, data equals data. And so what do I do now that I don't have the real data? Okay, so I still put in my model name here. Now sample.cove, it is always sample.cove. I know this is a correlation table, it's sample.cove no matter what. Okay. So in this example correlation table, sample.knobs, which just makes me laugh, but it's number of observations. You put in the number of participants or the number of people. Okay. And so that's how you can estimate without real data, is it will convert this correlation table to a covariance table, or if you have a covariance table, it will use that. Now, when we're running the model here, something I don't know that I made pretty clear last time, is to keep yourself straight from the model, like the definition of the model, and the fit of the model, which means like the output from the model. We're going to use this notation where we call whatever it is model.fit. That is where you're getting the output from the model versus building the model here. Because there are plenty of times where we're using the model, like when we run it, we use the model name, but then when we look at any of the output or make the pictures, we use the fit. And so those are easy to confuse because they're both models in a sense. So be sure you have like the definition of the model versus the fit of the model. So the book uses this notation, and I really like it, where you call whatever your model is model, but then always add .fit for your summary of the model. Okay. So ran that, seems to run okay. Now let's look at the summary. In this section we're going to add r squared equals true, so we can start always looking at those. Alright, so what happens? Well, we've got to look at degrees of freedom to see if we were correct, each path coefficient, that error variance, and our r squared values. So here's what happened. It says degrees of freedom equals 0. I said I had 10 because it's 4 times 5 divided by 2. And if we count, we've got 3 variances. 1, 2, 3 paths, 4, 5, 6, and an error variance. That's 7. What happened to the rest? Right? Well, here's the thing. One thing that I know I've said in a previous video, but is never clear until you make this mistake, is that the covariances between exogenous variables are automatically added in lavaan. So what does that mean? What that means is what it does is it automatically adds, let me add a little shape here, shape. Nope, show me the shapes. Is it automatically adds, this is close enough, these sorts of lines between the two. Okay. So it'll add a covariance between these two, a covariance between these two, and a covariance between these two. And you'll see that on the picture we'll build because that drawing did not work very well. But that adds 1 covariance, 2 covariance, 3 covariance. And so that ups us to 10. So it's 10 minus 10. So this is a just identified model, which is no good. But that's why sometimes it's hard to remember. If you didn't want these to be covaried, you can turn that off. And we'll get into that a little bit later. Right now we're just kind of learning the steps. But there is a way to make it where the covariance between these goes away, because if you don't want it. But that is an automatic thing, which is nice for confirmatory factor analysis, but maybe not so much in some of these other types of path models. So that's why degrees of freedom was wrong in a sense. But looking at the output here, I've got my y equals. That still uses the variable names from your matrix over here on the left, but then here's where it's stuck in the little labels. So those labels are just there to help you or later to impose constraints. All three paths are significant. It looks like the first two are strong and positive, and the second one's more of a weaker negative one. Okay. This is not a standardized solution though. Actually, because it's a correlation table, it is a standardized solution because correlation is already standardized. So these would be all in the same scale. Okay. It does estimate the error variance for y, so that should be positive. And my r squared out here for y is 0.95 because this is made up data. So we estimated 95% of the data in y. Okay. Last thing, let's make a picture. So we're going to use SimPath. It's going to be the model fit, not the model drawing, but model fit. What labels equals parameters. We could also do STD for standardized parameters. And let's try a tree layout this time. And so here's where you can see the thing that we forgot. So we've got the error variance here on y. All three are predicting into y, so there are path coefficients. And then it estimated the variance for each of these. So 1, 2, 3. And you'll see it's a standardized solution because the variance is estimated at 1. Okay, so anytime it has a little 1 out here, that means it's been standardized. And then it also estimated the covariance or the correlation between these two. And by estimated, I mean it took it straight from the table. Alright, but that is why our degrees of freedom were not correct. Alright, let's look at a second one. So this is the example from the book. It's a mediation example. So we've got years in school predicting salary, but we're also going to include cognitive ability on that. So on this particular example, we do need to include the labels for the paths so that we can estimate the indirect effect. Okay. And so indirect effect, I mean years to school through cognitive ability and predicting salary versus just having this path here. So it's very similar to comparing C and C prime to see if they're different. This is a purely exogenous variable, so it's going to have a variance we're estimating. So let's try degrees of freedom again. So 1, 2, 3 squares. 3 times 4, 12 divided by 2, 6. We're estimating 1, 2, 3 paths, right? 2 errors, and 1 variance. So I lost track already. 1, 2, 3, 4, 5, and the variance on years in school is 6. So this is also a just identified model. And now in these particular cases, it would be better to run this as a regression because just identified models are not good, but just kind of an example. So this is a covariance table. That data is on the bottom of page 31. And we only enter the bottom half of the table from that page. And you'll see that the numbers here on the diagonal, or on the ends of the triangle setup, are really large, and that's the variance for each question. Right, so this is a covariance table, so I'm going to run that. Got my data set up. Again, we have to name that matrix, so salary, school, and IQ. I'm going to click on it over here just to make sure that looks correct. I haven't screwed anything up. Right, nope, looks good. Now, if we're trying to define this model, what I tell you to do is, if you want, and see if you're getting this, is to pause me talking and see if you can do this model without looking. But really what I'm going to do, though, is I need to predict salary. So what's coming into salary? So I always start, when I'm doing these models, as far as I can to the right and work my way back. But you can start on the left and work your way forward, too. But since models are defined by y first, sometimes it's easier to start at the end of the train and work your way backwards. So here for salary, salary is going to be predicted by cognitive ability and years in school. So I'm going to do salary, tilde, IQ, and years in school. The arrow coming into cognitive ability is just from years in school. So I've got cognitive ability, tilde, years in school. And then years in school doesn't have any arrows coming into it. And so that's what we have. We have salary is predicted by school and IQ. If you have the original printing of the book, in the book itself, this is backwards and is incorrect. So just a warning. That's one of the errata from the book. We're predicting IQ with school. Right? So IQ predicted by school. And then this new thing. Okay, so I labeled each path A, C, and B. And we're going to do the indirect effect. So I called it end, or the book calls it end for indirect. And this little piece of code right here, this colon equals, is for specialty effects, like in this particular case, mediation, but also moderation. So we're going to say it's the indirect effect of B times C. Okay. And so B times C, as in years through cognitive ability predicting salary. Okay. That is actually the way the Sobel test works. It uses the paths here to determine if this path is different by including that variable. It seems a little odd because you're testing if this is changing, but you use these two paths to determine that. And so this particular colon equals is very specific to specialty effects. So this is one of the only times we'll do this, but I think it's useful to know if you're going to do interactions in regression. Okay. Or if you want to do a mediation analysis that's very complex and has lots of other things going on, this is how you might program that. So we've built our model. Now we're going to run the model. So we've got SEM of the model, our covariance table, still .cov, even though the last one was a correlation table, still .cov, and then the number of participants. So from the book, I'll run those three, and then let's look at the output. So we're going to look at our path coefficients, our indirect effect, R squared, and error variances. So we've got 0 degrees of freedom because we had possibly 6 and we estimated 6. And you can also count them. So 1, 2, 3, 4, 5, and then 6. Okay. Let's see here. So I've got my A and C paths, so they're both significant. B is also significant. I've got my 2 error variances, and then our parameter, our indirect effect parameter out here. Okay. Okie doke. So now I'm going to create a picture so I can see it. So here's, oh, it drew this kind of backwards. So here's school. So here's the variance for school, right? And then I've got the 2 paths here. My error variance is here. So you can tell that this one is exogenous because it's got the dashed lines. These 2 are error terms because they're solid lines. And so what it did was it kind of used the data to calculate this 8.61 that's pulled straight from the table and sort of gave us the indirect effect instead. Because in theory it should have calculated that variance for us, and we would have been screwed on the degrees of freedom. Right? Our 2 R squareds, we're doing okay. They're not great, right? But these are both what I would consider a medium and a large effect. And all of our paths are significant, including that indirect effect. So I would say mediation has happened, even though this isn't the best way to do mediation, probably, if that's your only goal, is a 3-triangle diagram for mediation. But it's an example of how you can take regression and put it into SEM and get the same answer. Alright, and we created the model picture for that. And so from this, you really should get the buildings of, like, what do I have to do to make one of these models happen? You have to enter the data in some form. You have to make sure the data is set up correctly. If you have a covariance or correlation table, give it names. You have to build the model. Right? That's one of the harder parts, I think. And then fit the model. So run the model and get the output look at the output, that's the summary function, build a picture, even if it's hideous, just to make sure that you've done what you expected to have done. Okay? With the warning that the different picture options will lay out your picture in a different way. So it won't always be what you drew or had in your mind. It will put them kind of however it wants. So those are some examples of regression in a path analysis style.